Bas is the head of the Hydraulic Engineering Laboratory at TU Delft, and it is located in the Netherlands. He has been researching, advising, and physically modeled coastal and hydraulic structures since 2000. He holds an MSc and a PhD from Delft University of Technology in the Netherlands, and he has extensive experience in solving coastal engineering challenges. Bas is presenting on novel measurement techniques for coastal structural armour layers. Bas, please, the floor is all yours.
Thank you, Jorge. Thank you for the introduction and for the invitation that I can share some slides with you the coming 10 minutes. So yeah, I've been working a long time in coastal engineering, mainly doing physical modeling on armor units. We like to have soft protections in the Netherlands, so where we can, we want soft protections. But here on the background, you can see, I hope you can see, yeah, are the slides visible? Yeah, excellent. So here you can see the entrance to the port of Rotterdam, where there's a lot of shipping. So there you cannot have a long beach. So there are places where we need these hard protections. And here there were recycled concrete cubes. So very.
Can you do it in full screen? We can only see a very small screen.
Oh, I thought it was full screen. This better?
Yes, now it is
okay.
better.
So here we can see the recycled concrete cubes that are used in the Rotterdam harbor. And this, yeah, the challenge and innovation I will be talking about are the measurement techniques that we can that we actually need also to develop if we develop new types of armor units. And this talk is based on cooperations we have with Delta Marine Consultants, Deltaris, and E-Concrete. So I will tell something about these new units, the new type of units that the last years have been coming up. And well, what do we measure about them extra? So I will have some examples about the slope parallel, the slope perpendicular dimension that we're measuring, and also the movements of the layer. And also in the end, if we get more knowledge, how do we share it together, which also can aid the innovation. And going towards the new type of unit, the past 20 years or 30 years, we were saying that the modern, the innovative type of unit was more like you see on the top, the acropods or the Xblocs, the single layer units that were placed in a single layer. That was the modern thing. But actually nowadays, different types of units are coming up. And here I show the E-Concrete coastal log units, and they are regularly placed together again, so not irregular. And then here we can see another example of these regularly placed single layer blocks. These are symbol cubes. They can also be placed together flatly on a single slope. And then, of course, there is the XblocPlus. I will show a picture later. That is also going very strong. That is also placed regularly in a single layer. And this is actually different than all the Xblocs and acropods 2 or acropods or core locks that were placed the decades before and are still being placed. Oh, I'm going a bit quick. And why do we want these regularly placed units? Well, actually, the placement of them is more straightforward. Actually, making something random is quite difficult for a crane operator. Also, because they are so tightly packed, they're actually quite strong. So yeah, you have a lower concrete use. The one particular part is that because they are nicely aligned, you have difficulties in placing the first row. So the first row, you need to be able to make a nice toe and place a first row easily. And because they are so nicely aligned, once you get some extracted block, so once you have initial damage, then the progression of damage can be very quick. So there are some particular things, but we can see that these things are used more and more and developed. And then if we look in the guidelines, actually, most damage parameters that we are looking at are still based on the old rock protections, where we have a few rocks that can be displaced. So we count the number of moving rocks, and that is then a damage prescriptor. But for these single layer things, then also even if one block is going out, we already call it failure quickly. And also the whole damage mechanism can be different, because actually these single layers look more like a dike slope. So as you can see here with the dike slope, it's very smooth. There are no drag forces. When the wave goes down, we get this uplift pressure from below. So actually the whole damage mechanism is completely different. So the vertical elevation needs to be measured, and not the single units that are extracted. So here we can see a nice 3D scan that we can make nowadays. This was a XblocPlus slope that was made with just taking what your iPhone 30 images, and then you put it in a computer and you get a really nice 3D image out of it. That sounds simple. Of course, you need to be careful because we want to see changes. So you have to align the before and after the test situation so that you can get a millimeter accurate vertical displacement of these blocks. And then you can see very interesting things. So for this XblocPlus slope, we saw that this is the top layer of the slope and the difference between two tests, so before and after a test. And then we can see that before we see any extraction, so the real damage to the layer, we can already see that the layer is going slowly up. So the material underneath is slowly going down. So you get this small start of damage. So we can see something happening. And the question is it allowed or not? But at least this is 1 or 2 test steps before you can see the actual extraction and the complete collapse of the structure. And for this, there are no accepted norms. So we don't know this is allowed or this is not allowed. But you can see it. And also the coastal lock, another nicely, this regularly placed single layer block. Apologies for the colors, they are inverted, but still here also around the waterline, you can see the layer just going up just before you get this big damage. And then you can also use this knowledge in design. So we know these uplift pressures are important. So we tested with e-concrete in our laboratory this initial design of nicely placed together blocks. And we saw if we increase from the left to the right, just the distance between the blocks, then you can see on the bottom right that the damage number, the critical damage number, went from about 2.5 for the lower waves to, well, 4, about, so almost twice as stable for the 10% spacing. And if you increase the spacing further, well, we know that we cannot break the slope anymore for the waves that we had in our flume. So we even don't know how stable it is. So you can hear what this knowledge on the uplift pressure was used to improve the design. There's other things that we have with these single layers, because they are so nicely placed and clamping each other tight. A lot of pressure is being placed on the lower row, so the toe layer. Yeah, so sometimes it can slide away. And now if you just take 2 pictures from above, so also using the camera as a measurement instruments, you can quite well see when it starts sliding a little bit forward, and you can again use that in the design. So on the top, the bottom right, you can see 4 types of toe with different friction and different amounts of rocks against the toe. And then in the slope, you can see for these protections really clearly, these were regular waves, so it should have been H and not HS. But you can see that the sliding of 10% of the block size, well, the resistance increases if you make it more rough or if you increase if you add some rocks. So again, another example. And this displacement is not only at the toe, you can even look at the entire structure. So here we see a round head of a single layer cube breakwater. And here we just look at all parts of the picture. So again, this measurement is only done by 2 images. And we can just correlate the pixels, and we see that due to the sliding of the toe here, this entire layer slides down a little bit, 20% of the diameter. And that will mean that on the side of this round head, the joints will open and it becomes a weak spot. And we can already see that before we see any extraction. So again, with 2 pictures, we can see the entire view of the displacements of the units. And we can also see that the origin of these displacements is the small sliding of the toe. And again, yeah, we can quantify it, but we don't know what the limit is. And then the last failure mechanism, this was actually for the irregularly placed blocks, like we can see here in Xbloc. So here innovation has kept up with it. So we made a nice measurements technique for rocking, but then the rocking is not a big issue anymore for the new places. And due to rocking, these cubes or the units, they can break. So here we can see that the leg of the Xbloc has fallen off. But of course, it's not only the Xbloc, we also see it with the core lock, and we also see it with the acropods. When there's space to move, sometimes this unreinforced concrete can break. And if you want to measure this in a small scale model, that is actually, well, hard, practically impossible. But what is possible is to measure velocities. So nowadays we can take a small computer where the measurement instruments are included that are in our mobile phone. And we were able to 3D print an Xbloc and put this whole computer in there with a watertight USB connection to get the data out and the power in. And this the first technique was measured, and here we can see some experiments of a nice Xbloc slope, the classic Xbloc, and we can here see the instrumented units. You can see, for instance, though it was not the instrument one, but the blue one in the middle. You can clearly see the rocking motion of these blocks, and the ones with the instruments, we measure all the displacements, and then you can get images like this. So you get 3 components of the linear acceleration and 3 components of the rotational velocity, and well, we can combine that, or we will publish that soon in a journal, that you can get like the characteristic impact velocity with which this one unit touches the other one. So again, another failure mechanism that you can quantify. So a lot of research is going on. So what can we do? Most of this research we do with master students, and over the last decades we were cooperating with companies and doing our own research with more than 30 master students. So this takes a lot of education, and the nice thing is also with the cooperation with companies like BAM, they are very open and everything is published online in these repositories, so everybody can check this research. And also to a more higher scientific level, we also started a journal, this Diamond open source, so you don't have to pay for the access. So also these kinds of innovations can now be published without ridiculously high fees for publishers. So we are planning to publish this rocking research in this, for instance. So that brings me to my last slide. So development of armour units typically is done in-house in companies. And that means that the design approach, the safety factors, the exact things, they are only known to that company, and that can hinder innovation or acceptance of a thing. So, although the products are good, here we can see a 30-kilometer long dike that has been made with 2 types of innovative blocks, and it's perfect and it's completely tested. But still, scientific description of all the processes and making exactly quantitative design guidelines, I think, will further the innovation and speed it up, and lead to a quicker acceptance. And I think that these measurement techniques, as I showed them, they can help in this acceptance of units, and also to have to pinpoint more the real problems that come to the new problems that come along with new products. And I do think that open sharing, as we are doing and promoting, also further increases this acceptance. So that was, only about the top layer of the armour units, very quickly, but I only had 10 minutes. So I hope it was not too fast. Thank you for your attention. And later on, I will be answering some questions.
Thank you. Thanks a lot, Bas. Excellent presentation. And well, I will continue and following in the presentation of Bas. We introduce our second speaker, Jeroen van den Bos. But before introducing Jeroen, I really encourage the audience to send the questions for our speakers. And well, introducing Jeroen. Jeroen is a senior coastal engineer in Royal Boskalis. Jeroen holds an MSc in civil engineering, and he has over 20 years experience as a designer and large-scale project engineer in the maritime construction industry. As a senior coastal engineer, he designs breakwaters, bed protections, shoreline protections, and offshore scar protections. And he is also a part-time guest lecturer at TU Delft. Jeroen is today presenting on the numerical modeling in coastal structures design. Jeroen, please, all yours.
Thank you, Jorge. I will start with sharing my screen as well. Good day, everybody. Morning, evening, where are you in the world? As Jorge said, my name is Jeroen van den Bos. Indeed, I've been working in this field for about 20 years as a designer of breakwaters, and I'm also part-time at the university. And so I'm a little bit in between the academia and the practical field, and you'll see that in my presentation as well. I'd like to show you some things that are happening in both sides of my professional life and see how they match up. In case you're wondering about my employer, you probably know us. We're one of the largest maritime contractors out there, based in the Netherlands, where I am at the moment. And we have our own in-house engineering department, meaning we make our own designs for our works, and that's where I work most of the time. That's also the logo you'll see most of my slides. What my topic is about, that comes down to a phone call that I had from Jorge at the beginning of the year when he asked me to join this webinar. And I was a little bit reluctant because I said, well, I don't have anything that I'm particularly working on, so I don't know what to present. And Jorge said, oh, you've been doing a lot of stuff about numerical modeling. I said, yeah, I did a couple of years ago, but I don't do a lot of that stuff anymore. There's all kinds of reasons why that development is stalling a little bit. And Jorge said very cleverly, well, then present that story. Say what you see with numerical modeling, why you were working on the subject all that time ago, and tell about what trickles down to your normal everyday work, and let's discuss that in the panel. And then I made a mistake. I said, yeah, sure, that sounds like a good idea to actually present. So here we are. In the next couple of minutes, I'll try to present to you something that I have not been working on for quite a long time. So we'll see how that works out. But at least I'll try to show you what I see happening and why I think that is the situation. Yeah, so what kind of models am I talking about? There's, of course, lots of numerical models, CFD models out there. In my talk, I'd like to narrow it down to this type of breakwater design models. So suppose that the waves are coming in this case, from the left side of the picture and crashing onto the breakwater. We'd like to design that breakwater. We don't know what size of armor unit, how high it should be, etc. So there's computer models out there who can actually help you in that process. The one that I'm most familiar with is OpenFOAM, and you'll see most of my examples are from OpenFOAM. But of course, there are other models available, and I'm sure that in our quite large audience, there's lots of people who are thinking, yeah, I know another model. So please let us know in the discussion if you want to join the discussion. But my examples for the time being are from OpenFOAM, and also, because of the time, I'll narrow it down to this rubber mount type of breakwater design. Of course, you can also try to apply these type of models to scour protections, offshore protections, casing types, etc. But today, I'd like to focus on these rubber mount structures only. So why, at least a couple of years ago, I was so enthusiastic about this whole development? What's the potential for these type of models? Well, at the moment, as designers, we have basically two sets of tools. We can use the empirical formulas that you find in your design manuals, in the ROC manual, coastal engineering manual, wherever you are in the world, whatever you're used to applying. And you can go to the lab to do physical models, maybe supplemented with field measurements, but those are the two tools that you have. And wouldn't it be nice if you have a third tool where you can just run it on your computer? Most of the empirical formulas are based on generalized structures, but there's always something specific. Maybe you have like a berm or a strange foreshore, or wouldn't it be nice to model every single case that you're trying to design just in the quiet of your own office on your own computer, see what happens, and then draw conclusions from that, and then supplement that with the other two ways of engineering. So you have three tools instead of two. Maybe you could look at overtopping. Maybe you could even go as far, look to armor stability and design your whole project just on your computer. That would be great. Of course, you always have to see that in that triangle. So you always have a combination with the other methods, especially with physical modeling. There must be some kind of calibration involved. Maybe you can use it to extrapolate between physical models that you're doing. So instead of doing 10 physical models, you can do 2 and do the other 8 in between with your computer model. Maybe you can add to your physical models, because in physical modeling, you cannot actually measure every single thing at every single spot. So maybe you can just increase your spatial resolution or your temporal resolution with computer modeling. And another reason why I think it could be a nice way of working in my environment, from a contracting and commercial environment. We do projects, we do tenders. We can do it in-house. We can open it up ourselves. We don't have to go to nice people and good colleagues of laboratories in a very early stage. We can have a bit of a look around ourselves and do a quick scan. especially in early design stages when there may not be a project yet, there may not be a budget yet, there may not be time to go to a lab and study things in detail. So we can use a separate tool to have a look in advance. So these are the main three things why it could be a potential tool. Now, what do I see happening? Let's first look at the academy side and then look at the practical side afterwards. In literature, if you read through, for instance, because you're asked to give a talk about it in the weekend before, you think, well, let's read some literature to actually get some idea. There's a lot of papers being published. There's a lot of stuff happening. There's people adding new models, new parts of models, new modules. You see a lot of validation against model tests. You see, like the paper I'm quoting here, where you see comparative studies between various numerical models, OpenFOAM against the SPH in this case, and even a completely different type of model, SWASH, for all kinds of applications in increasing complexity. Still mainly, what I see on the hydraulic side of the equation, just the water motion, so how the waves react to the breakwater, not yet the other way around. So you don't see a lot of stability or deformation of your breakwater being studied, but at least you're trying to get the water motion right. And you see some description of, say, what I call best practices, so practical guidelines about grid size, flume length, computation time, etc. I've put a question mark there, not because I'm doubting that these practices are good, but because you don't see a lot in literature to these more practical things. These things I've run it on 20 cores and it took me 6 hours, and I've used a grid size of so and so much. So it's a little bit difficult to get that information from literature, but you see this happening. The main conclusions that I draw from these developments is that it is quite possible. These models are capable of reproducing physical model tests to a quite close degree. Computational effort that I see happening is still quite large. We'll get to that in a minute as well on my other slides. And you do see that most of the conclusions are still based on a calibration based on numerical models, on physical models. So just off-the-shelf application of numerical models without any calibration is not yet done in what I see. So there's always this double system. And we did some work on that as well. Just a few examples in our own group at the university. I won't go through the details of everything in particular, but you get an overview here. So we had these students doing their master thesis, looking at things like overtopping, even some stability of armour units, not directly in the wave model, but they took the boundary conditions, velocities from the wave model, then put that in a flow model, and actually were able to calculate some forces. You see a calibration on overtopping that works quite nicely. And even for rather complicated storage like the bottom picture, where we have a breakwater in front of a key wall, a vertical structure, and we want to model the water motion across both structures and even in between. That kind of works. Most of these students manage to get their model working. But I'm sure that most people in the audience have done their MSc thesis themselves and know that it takes like 6 months. So at the end of their studies, these students were able to take all that time and really think in a model and get it and reproduce the results. Mostly done also with irregular wave fields, about 500 waves, all 2D. And then you talk about simulation times in the order of days, so that's still manageable within the context of a student thesis. So that kind of supplements the other literature that's out there, that with careful calibration and a lot of time and effort, you can manage to get reasonable results out of these models. But now let's move on to the practical side, where I work. So this kind of thing, where somebody just says, well, let's talk about the design for this project, and I've run a numerical model, let's draw some conclusions from it. I don't see that happening yet. Here at our own company, we are able to run these models. We have them available. We've set up the computing system for it. We have a few people, including myself, who are capable of running these things. But it is a little bit of what I call the hobby stage. We're looking ahead of it. We can do it a little bit, but we're not using it in everyday practice. That's partly due because it's quite a long learning curve to set it up. So in just the design for our projects and tenders, it's not a go-to tool. It's not a part of our way of working. Sometimes, but that's the exception, on very large projects, we tend to go for a numerical model just as a, what I call exploratory stage. So we've done maybe already physical model testing. We want to study something in particular. Let's run a numerical model to see where we go. But we are not using that model yet to go to our client and use it as a main tool. Say, listen, we run computer model, here's the results, so please accept our design. That's not working yet. The third thing is we do see it increasingly in research proposals where we are asked to join research programs. There's usually a work package on numerical modeling next to physical and field measurement. So you see it happening there. But in my daily work here at the engineering department, it's not yet common practice. And why not? Well, the main reason perhaps is it does require quite advanced computing skills. You're working with large quantities of data. You may have to go for cloud computing. It's all Linux based, and you may not be familiar with that. The models are, say, in varying degrees of user friendliness, depending on which model you choose. There may be a manual, there may not be a manual, maybe a graphical user interface, there may not be. It's not really off the shelf, plug and play, and start playing with your results. So it requires quite a big setup. It also adds to your skill set as a coastal engineer. As breakwater designers, we, as I always say, we already have a job, so we're thinking of stability and all these calculations. And if you go down the rabbit hole of numerical modeling, you'll find yourself in discussion of turbulence closure all of a sudden, or grid convergence, which is not in your normal skill set. So you have to learn and work with that as well, which takes a little bit of time. The computational effort is still quite prohibitive. I said in the beginning, it would be nice to do these kind of things, say, in advance, in early stages of the project without going to a lab. And then if it takes a couple of days to run a case or even a week, then you're still losing that opportunity. So for those quick ideas where you have, at least in the way that I work in our company, where you have the opportunity to use the model, and the computational effort is still too long, basically, to meet that opportunity. Of course, you're still dependent on physical models, which I think we may discuss in the panel discussion. I think it's a good thing in the end, but it also means that these quick scans without any calibration may or may not be worth it yet. And the acceptance is still not there. So even if I would make a final design based on a CFD model, and I go to my client and say, this is the picture, then it's not as easy to get it accepted compared to having used a numerical or a physical model. I also think that the community is maybe not there. Best practices are not very clear. So it's so difficult for us to learn from others and say, well, if you've used the grid of 150th of the wavelength, oh, that's a good thing. Let's do that as well. So you have to basically rediscover everything yourself as well. And that makes it also a little bit difficult to get going. And maybe there's other reasons. This is typically something that we can discuss in the upcoming discussion. So please, also from the audience, if you have an opinion on this, let us know. I'd like to close my presentation with an example and maybe a little poll as well. Because this is something that I have been working on for the last couple of weeks and months. It's something that draws my attention at the moment. Let's look at artificial reef elements. And I know there's a lot of different reefs out there. So that's for the generalization of this talk. Let's assume that we have devised our own new reef element that just happens to look a little bit like our company logo, but that's pure coincidence. Suppose we have a concrete block like this and we want to design it. And say, as part of the design process, we'd like to know how stable it is under a wave. And let's say that we want to do this with a numerical model. So we want to be able to run a wave across it and maybe find the forces on the unit, maybe find some velocities inside to see how well it reduces the waves, and maybe it provides a real habitat for ecological growth. And maybe we want to do some more complicated stuff like scour or flow. The funny thing is that if I talk to people who are developing these kind of blocks, and they may come from a non-engineering background, and they are more or less expecting that we already can do this. They come to me and say, Jeroen, I've got this block. If I send you the AutoCAD for the drawing, can you put it in your computer and tell me if it's stable or not? But then I have to explain to them that that's not the way we work yet. But the people out there are somehow having the picture that this is a normal engineering practice. And I find that very inspiring, because you could turn the question around, why are we indeed not doing it that way? Maybe that's the logical approach. So my main question for the discussion, suppose if we take this example, when do you think we will be able to do this in a numerical model and design the stability and help support the innovation for these types of blocks using numerical models? So that's my question to you. We have a small audience poll to maybe kickstart the discussion. Also, if you can open the poll, please, and we can ask the audience to join, and then we have some kind of idea. So my question is, what do you think when we can actually do it? And then I mean, do this in an easy engineering everyday practice kind of way. So you can see the answers on the screen. We have like 10 seconds to make up your mind, because I want to have your gut feeling. Don't think about it too long, and then we see the results in 10 seconds. So please let me have your votes. And also, if you're ready after the results, just show them on the screen. Okay, that's nice. That's almost like a normal distribution. And that's a lot of people think we already can. I'd like to hear from you in the comments and see where we are. My own personal answer would be roughly 1 to 2 years, depending on how serious you want to do it. So great. Let's take this on board in the panel discussion, and then that concludes my presentation for now, Jorge. So we can move on.
Fantastic presentation. Thanks a lot, Jeroen.
Thank you.
And we will follow with the presentation of our third speaker, Pieter Bakker, and we will also introduce Bas Reedijk, who will join us later for the questions and the panel discussion. Bas and Pieter work for Delta Marine Consultants, the DMC-BAM Infraconsult, where Bas is the head of coastal engineering and water management, and Pieter is the Xbloc Global Manager. The two of them combined have over 50 years of experience in coastal engineering. Bas is a creator, designer, and researcher, and he has published several scientific articles, and he is known as the main inventor of the recognized Xbloc, between other inventions. Pieter has extensive technical expertise in coastal engineering and practical experience in marine construction and in overseeing breakwater and redevelopment projects worldwide. The two are part of a team that developed the Xbloc and more recently developed the XblocPlus. Pieter is presenting on multifunctional wave protection, and Pieter, please, all the floor is yours.
Thanks, Jorge. Yes, I will dig right in. So I'm speaking about wave protection, and just to start, why do we need wave protection in the first place? We've been doing projects with breakwaters and shore protections for, well, I'm doing this for 20 years now. And typically our projects were ports, infrastructure in the sea, along the sea, airports, etc. But more and more we see that the challenge lies with adapting to climate change. And as I have shown in this sheet, 40% of the world population lives close to the coastline. 10% of the world's population lives in a low-lying area, rather low-lying. Personally, I live in the lowest point of the Netherlands, so I count myself within these 10%. And 1% of the people live in the small island developing state. So for them, it's why wave protection is really a fundamental choice, fundamental problem that needs to be solved. Then if you do need protection against waves, you have options. And I don't know, I don't want to do a poll because I think if I ask you which option you prefer, everybody will go for the left one. We all like a beach and nobody likes a gray wall, which is not that appealing. So in the task that is ahead of us to adapt to climate change, there's options. And the first choice that we would make is to go for a soft solution, like dunes or mangroves or sand nourishment. This is the most beautiful solution, but you need space for that. And it's not always possible. So if that's not possible, the next option would be to go to a hybrid solution. So to combine the benefits of hard armor, hard structures, with the benefits of soft solutions. And in my opinion, that's a type of project that we will see a lot in the coming years. And the third option, which still also will be needed quite a lot, is a fully hard armored wave protection. Because in many options, like the small island states, there's simply no space for this soft structure or the hybrid structure. So there will also be a lot of hard armor projects. So they will be there, and in that, with that given fact, we will try to focus on making these hard armor projects as positive for all the stakeholders as possible. So what we focus on is on resilience to climate change, because that's what was the task to adapt to climate change. Of course, it has to be affordable, so economics play a part. We focus on ecology and biodiversity, sustainability, clearly. And also now aesthetics become more and more important than, let's say, 20 years ago. Then a breakwater could look whatever, as long as it would break the waves. And now people also like a breakwater that looks nice. And for us, it's important to keep on innovating. Every time we try to squeeze out carbon or cost and improve constructability. So for us, it's something that we keep on doing. So yes, we've been working in this field for quite long already, 20 years. On the left-hand side is the original Xbloc, on the right-hand side, the XblocPlus, just to give you an impression what these blocks look like. And yes, one thing that we focus on is reliability and resilience to climate change. I'm going very quick. I'm not going through all the details of this slide. I only want to point out that with the original Xbloc, we had a resilience which was about 25% on the wave height, which is this blue arrow. And with XblocPlus, we have gone to a much bigger resilience. So we are much more capable to withstand waves if they would exceed what we expect now. And I'm going to click a few times to go a bit quicker. But I hope you get that from this slide. So we are able to withstand waves which are far exceeding the design. As a result of that, with this system, we also need a lot less maintenance. So in this slide, I compare a seawall in the UK, which is designed with rock, 6 to 10 ton armor. And we exchange that by 1.5 cubic meter XblocPlus units. You can see already from this figure that there's in the quantities a big impact there. But what is very relevant is that the rock structure will need maintenance in its lifetime. And especially if we do get climate change, for this particular project, we knew the predicted future wave climate. This structure would most likely need 3 repair operations in a 50 years lifetime. And with the XblocPlus structure, you do not need that maintenance, not in the current wave climate, and also not in the future wave climate. Well, as I said, you already see for this structure that the material quantities are significantly lower, and that also translates into construction cost saving. And in the UK, most of the big rock comes from Norway, so there's a big cost component in the transport of these rocks. And the concrete structure is about half the price of the rock structure. Then we try to make our blocks as ecological as possible. So what we try to do is to do the mitigating measures in the structure rather than to somewhere else make a reef to compensate for the negative impact of a project. So we try to not use new raw materials somewhere else, but to do the mitigating measures in the project. It's done by 3 ways. So by changing the chemical composition of the concrete to make it less unattractive or more attractive for marine life. by increasing the rugosity of the surface so that larvae can attach to it, and by changing the macro design of the blocks, so it creates also protection for the organisms. Just some pictures of the projects that we are doing. So that's what I want to show on the biodiversity side. But as I said, also sustainability is an important aspect, and mainly this is in saving material quantities. So in this slide, you see again the same example where, as I said, the rock in the UK comes from Norway, which has a big impact on the carbon footprint of that material. So even though concrete has a high carbon emission in the product itself, due to the reduced quantity, the overall emission of this concrete solution is lower than the rock solution. And we did some other examples which all show the same trend. And on the Afsluitdijk project, we reduced the carbon footprint of the armour by 56%. So by doing a smarter design, we try to squeeze out also carbon from the projects. So that's in quantity. We also are looking at options with the whole concrete industry. This is not something that we are very unique in. We, together with all partners, we are looking for concrete which has a lower carbon footprint itself. So together with Rijkswaterstaat, we are doing trials on the Afsluitdijk with different concrete mixes. And these will be monitored to see how they perform in seawater conditions to speed up the acceptance of these mixed designs by the Dutch government. And then the aesthetics, I said, in my opinion, it's nice if your projects have if they look nice. So I just have some pictures what this looks like. This is the Afsluitdijk. This is the project on La Réunion, where we are protecting the airport. Same project from the other side. This is a breakwater in Poland, which we completed 4 weeks ago. Which is, it looks like a computer animation, but it's a real picture. I think, and you can see how the breakwater does its function, because inside the basin it's really very calm. And this is the same project. So aesthetics, it's up to you, but I think it looks nice. And one thing I wanted to add is we are preparing for a project in New Zealand where also the aesthetics were important, but then in a way that it is the objective is to make it to make it look less man-made, and there's a solution for that we're going to apply there, which is, in my opinion, very nice, because this also adds to the, it blends in better in a natural environment. So to summarize all that, what we've tried to do is for all the stakeholders in a project to make a positive contribution with these blocks, from the designer to the owner, but also to the environment and to the people who live nearby a project or who will fish there or walk or cycle, etc. So this is something that, in my opinion, is now very important. And 20 years ago, you could just have built a grey dam in the sea and nobody would really have cared at that time. I don't know how I'm on time. I'll go very quickly. As I said, we want to continue with innovating, and within our system, we've developed a new block which combines with it to reduce wave overtopping. I'll go very quick. So what these blocks do, they add roughness to the design right at the position where it's most effective. And this translates into a roughness coefficient, which is a function of the relative freeboard, a bit in detail maybe. But as a result, we can lower a breakwater. And in this example, it's only 90 centimeters. 90 centimeters, is that so important? But it gives you a very big and relevant saving in your rock material and a little bit in concrete. And also that, again, it squeezes out a little bit of the cost and of the carbon and of the time to build your breakwater. So this is things that we are doing to continue innovating and improve the system. That's it, what I wanted to say. There's some sources you can click on for more information, but that's it for now. Thanks for listening.
Thank you. Thanks a lot, Peter. Great presentation. And yeah, we are running a little bit out of time after the schedule, but we have quite some questions. So we can start with the Q&As. For example, we have one question for you, Bas Hofland. if you could choose to have one, what do you think that can be a great innovation for making measurements or performing physical model tests?
Thanks, Jorge, and thanks for the question. Yeah, so we talked a lot, and a lot of innovations are now on the ecology side. So of course, we all also in the small scale we would like to measure a lot on these ecological values of blocks. And what we can measure is velocities. With PIV systems, you can get entire velocity fields, turbulence, and that would be correlated to which species can live somewhere and which plants can adhere or are torn off. But I think before we can really develop that for the small scale models, we need to go to the field, because so I don't know of many biological measurements where they really quantify what a species a coastal species can withstand in the coast. So we don't have the target values. So we don't know which velocity or which pressure will enable a certain species to live somewhere. So I think that is the challenge, to go into these ecological things. Maybe one example, sometimes you can do something. For the wind farms, they were looking at the size of the rocks. And there you could really geometrically see that if we make one size of rock bigger, then the holes will be so big, then we can get lobsters in. So there we can really quantify, if we take this rock, then we get these lobsters. But for velocities, I think that is still the challenge for the measurements.
Yeah, thank you. And we have another question for you. Can the novel measurement techniques that you showed be used in practical projects, or are they too difficult, like much of the CFD models that Jeroen presented?
Yeah, so like Jeroen said, it's the computer models, they are possible, but they take a long time to get working. And I think the same is if you have these 3D elevation models, that is still some and I think a laboratory will think twice to make these very big scans. They are being done nowadays. So I think that's almost possible. And the nice thing about these techniques of the settlements of the blocks, they are based on only 2 pictures. So they are really straightforward. And I know I came from Deltaris, and there we are still, or they are now using this technique really to show in the reports the movement. So it's already helping to quantify these damages.
Okay, thank you. Jeroen, we have one question for you. Could we consider the CFD models to produce measurements in combination with physical model tests? I mean, could we shorten the time of physical modeling by assessing, for example, overtopping or reflection of a structure by performing numerical modeling?
Yes, I think we can. As I said in my presentation, I always see it in combination. I think numerical models would be capable of interpolating between physical models. Numerical models could be used for that. At the other hand, if you're already doing a physical model itself, you're automatically measuring reflection and overtopping perhaps in the same model. So I don't see a direct application to use the physical model only for armor stability, and then for the same conditions use a numerical model for overtopping. You could measure it in a physical model. But I see it in between physical models. If you have to do like 10 different cases, you can maybe just do 2 or 3 in a physical model, calibrate your numerical model, and then do the others in between numerically. So they can supplement each other there.
Okay, nice. And yeah, in the same line, is it always necessary to validate a numerical model with a physical model?
At the moment, for what I see from my own experience and in literature so far, yes. It will depend on the application. If you're just looking at waves and you may have a non-porous structure, and then maybe without any calibration, but as soon as porous structures are involved, then you require calibration on physical model results.
Yeah. Okay, thanks a lot. We have also some questions for Pieter and Bas. Pieter and Bas, question for you both. With all your experience in developing coastal armor units, what do you think that has been the most important innovation in the field of the single layer armor units?
Yeah, for us, it's that we have gone from a single layer armor, which is random placement, so the orientation of each block is different. And now we have gone to interlocking armor with regular placement. And with this regular placement, we do not have a rocking anymore. When you place Xbloc with each block having a different orientation, you always have a few blocks which are not perfectly interlocked. Now, we avoid that by having a regular placement.
Yeah. And another question for you both. What do you think that can be the most or the next important challenge in the design with single layer armor units?
Yeah, the most important is to incorporate ecology in the system. So I'm a civil engineer, and yeah, we always design just concrete structures to withstand waves. But yeah, basically everything which we place in the sea, we should think about sea life and how we can improve the structure to form habitats for sea life.
Fantastic. Thanks a lot for the responses. Andrew, I think that we have also quite some questions from the audience.
Yes, we've got several dozen, so we'll do our best to address as many as we can in the remaining time, or a lot of time. I'm assuming we're not continuing with the panel, correct? We'll close out with the...
Yeah, I think that we do not have sufficient time.
Yeah. So one question that came across for Bas is what was the porosity rate of the physical model, and also why were the chains along the side of the wave flume in one of the photos that you showed?
I suppose it is this, Bas. So the practical questions about the modeling. So this porosity of the coastal lock units from e-concretes, that was actually the amount of space that is open. So and for a squarish thing, so if you put them 5% of the diameter apart, then also 5% of the space is open. So that was the porosity. And yeah, on the sides of a flume, when you do testing, you always have a little bit weaker spots, or often have a little bit weaker spots. So we just put high density change there to make the site stable. So you're really testing the middle part, which has the representative strength of a real structure.
Great, thank you. And the next for Jeroen, have you ever modeled, investigated rock armor stability in open foam numerical model? And also, what do you see as the main limitations with numerical modeling?
Or maybe that second question is an answer to the first one. I have not done that myself yet, armor stability modeling. One of the limitations of the models that I work with is that you cannot change the grid. So you cannot really actually move armor stones up and down. You cannot resolve the forces, and there's no coupling between, say, the grid, the armor representing the armor, and the hydraulic forces. So in that aspect, it's quite difficult to actually model armor stability. One way out of it could be to get your velocities and pressures perhaps locally from a numerical model, and use those to calculate armor stability in a separate way. But integrated in the same model, I've not done it. I think it's possible in a very complicated 3D way, but not in my practice yet.
Great, thank you. And this next one will be for you, Pieter. So the question is that we seem to be merely setting the concrete or rock directly on the seabed. What is typically done considering the geotechnical situation?
Well, basically, before you build a breakwater, you do soil investigations to see the type of bed material you have and subsoil. And based on that, you will design your breakwater either with a steep slope, if you have good soil, which is the most economical and the least material use, or you go for a flatter slope, or you have to do some ground improvement or soil replacement. So first you measure, and then you adapt your design.
Great. Another question for you, Pieter, is, and I suppose you did address this, but maybe you could touch upon the importance of some of the aspects, but how would you define the resilience in these structures? And it was also asked, you know, with in regards to the ecologically enhanced concrete, questions in regards to its makeup and the pH. But again, I believe you did address some of that within your discussion.
Sorry, I don't understand your question. Sorry, can you rephrase it maybe?
Yes. So in general, I suppose we'll start with the first. Is how would you define resilience in these structures?
Well, what we do, with the physical model, you test where you start seeing damage in a structure. And what we've chosen to do is make sure that our damage is that far away from the design condition that you expect, that even if, let's say, hurricanes come to the Netherlands, let's hope they don't, our structures will still be there. So we over-design, but still we squeeze on material quantity, on carbon, and on cost.
Great, thank you. And this next one is for Bas. It says, can you please expand a little on the developments or the research being made in terms of establishing criteria for the damage initiation before the extractions of the units for single layer regularly placed concrete armor units in regards to settlement and displacement?
Yeah, thanks. So what we I had one paper. It is linked in the presentation. I think everybody can download that later. So we just looked at when we saw the test before we saw actual damage of extraction, and then typically we could see settlements downwards of about 0. Yeah, I'm not exactly, about half the nominal diameter of the unit. So when they're sliding about half a unit, typically you get some open spaces that are, well, really critical. But these were types of settlements that were induced by the toe itself. So the main thing, actually, as a researcher, it's boring, I have to say. More research is needed. But if I had to put a figure on it now, but this is a completely not accepted thing based on one conference proceeding, it would be half a diameter of sliding. That would for me be coming in the critical area.
Great, thank you. And I see we're coming up on the hour already, so I don't know if you want me to do one more question or would like to close out.
Yeah, I think that we can wrap up. I think that it's been yeah. I would like just to thank you all our speakers, Bas Hofland, Jeroen van den Bos, Bas Reedijk, and Pieter Bakker, for this really nice and insightful webinar. I have personally enjoyed it a lot, and I hope that all our audience really enjoyed it as well. And thank you all our audience for attending today this webinar, and keep tuned because we will continue with our series of webinars in November. And see you next time. Thank you.